In the last video, we talked about primitive polynomials and proved a very important theorem called Gauss Lemma. And in this video, we are going to finish that circle of ideas and show that the polynomial ring over integers in one variable, polynomial ring in one variable over the integers is a UFD. So let me start today's video by recalling the proposition we proved at the end of the last video. We showed that any rational polynomial which has positive degree can be written uniquely as a product of a rational number and a primitive polynomial. C is a rational number, F0 is a primitive integer polynomial. Remember, primitive by definition means it's an integer polynomial, and this expression is unique, and C is then called the content of F. Okay, so this is an important proposition for us. So today we are going to start with the following proposition, which is the key proposition that we are going to use to prove that the polynomial ring Zx is a UFD. So the proposition says the following. Let's say f and g are two polynomials over integers. Let f and g be in Zx with f primitive. F is primitive. Then if f divides g in Qx, then f divides g in Zx. This is the important proposition for us. If a primitive polynomial divides an integer polynomial in Qx, actually it divides in Zx itself. So before we start the proof, let me quickly recall what it means for division to happen in a certain ring. If f divides g in Qx, remember this means, by definition, this means there exists a rational polynomial h in Qx such that fh is equal to g, right? If an element divides another element in a ring R, that means there is the third ring element such that the first element times the third element is the second element. So here the crucial thing is fh is in Qx. So now what is the meaning of the same thing, right? F divides g in Zx means, by definition, this means there exists h possibly different in Zx such that fh is equal to g. So the crucial difference between dividing in Qx and Zx is that this h may live only in Qx. In this case, we only say f divides g in Qx, but if it also lives in Zx, we say f divides g in Zx. So this is a very easy proof, but main thing to keep in mind is the difference between division in Qx and division in Zx. So we know that this is a hypothesis, right? We are given that f divides g in Qx. So we know that there is a rational polynomial h such that fh is z. Now using the previous proposition, we write h as c times h0, where c is in Q, which is the content of h, and h0 is primitive. Remember, this is a crucial proposition that we proved at the end of last video. Every rational polynomial can be written as a product of a rational number and a primitive polynomial, and it's a unique expression. So now we know that fh, or rather g, is equal to fh, which is equal to f, we can write it like this, c f h0. Now I am going to recall for you the Gauss Lemma. What is Gauss Lemma? Remember, that was a crucial theorem from the last video. Gauss Lemma says that if f and h are primitive, if f and h0 are both primitive, fh0 is primitive. Gauss Lemma says simply that product of primitive polynomials is primitive. So if two primitive polynomials are there, their product is also primitive. So in other words, this is primitive, because h0 is primitive by construction, f is primitive by hypothesis. So g equal to cfh0 must be the unique expression of g as a rational number times a primitive polynomial. That means c is the content of f, content of g, right? C is the content of g, and note that g is actually in Zx. Remember, that is a hypothesis. The crucial thing is f and g are both integer polynomials. So g is in zx, that means c which is the content must be an integer. This is something that we proved in the last proposition. We can write every rational polynomial as a content, which is in general a rational number times a primitive polynomial, but the polynomial we started with is rational. If the polynomial we started with is actually integer polynomial, then the content is actually an integer. Now c is in z and h, remember, is c times h0. h0 is an integer polynomial because h0 is primitive. C we have just concluded is an integer, so h itself is in zx, and hence f divides g in zx. That's all. So very simple proof, right? So this is a very simple proof, and it shows that division in qx implies division in zx. But the important two things to remember, both polynomials in question are integer polynomials and the first polynomial is primitive. That is very important. Only under that situation, division in qx implies division in fx. Division in qx implies division in zx. Now I am going to prove a nice fact before we finally prove that zx is a UFD. So I am going to call this a different proposition. It says that let fx be an irreducible polynomial. Let fx be an irreducible polynomial in zx with positive leading coefficient. So I am going to take an irreducible polynomial. Remember, irreducible in zx. It is irreducible in zx means what? When you write it as a product of, when you write f as a product of two other polynomials, one of them must be a unit, because irreducible means it has no proper factorization. So suppose also that it is positive leading coefficient. Then one of the following holds. One of the following holds. One is degree of f is 0. This is possible, in which case f x, which is actually in z now, is a prime integer. So one possibility is it is a constant polynomial, in which case it must be a prime number. Second possibility is it's not constant, in other words its degree is positive. Then f is actually a primitive polynomial and more importantly, f is irreducible in qx. So the hypothesis is that it's irreducible in zx, but it's actually also irreducible in qx. So let's prove this quickly. This is again not difficult given whatever we have done so far. So we'll first consider the case. First assume that actually we know that let me say that like this. Write f as cf0, where c is the content of f and f0 is primitive. Remember, we can write every rational polynomial as a product of a rational number and a primitive polynomial. In particular, we can write every integer polynomial as a product of an integer and a primitive polynomial. Of course, c is in z here because f is an integer polynomial. Now, if degree f is 0, remember degree f will be equal to degree f0 because c is a constant. So by multiplying by a constant, we do not change the degree. C is of course non-zero. So degree of f is 0, that means f0 must be 1, right? Because f0 is a, so in other words there is no f0. So when you factor it in terms of into unit and a primitive polynomial, there is no f0. That means f is actually c. So f is c, and when is an integer irreducible? Is an irreducible polynomial. That means, so that means this proves that f is a prime integer, because for example we can simply use the fact that the ring of integers is a PID. So an element is irreducible if and only if it's prime. So f is an irreducible polynomial of degree 0. That means it's an irreducible integer. An irreducible integer is prime, because in the ring of integers, irreducible automatically implies prime. So now we consider the second case. Degree of f is positive. But that means in this case c must be 0. Sorry, c must be 1, because if c is not 1, remember c is an integer, f is irreducible. So either c is 1 or f0 is 1. So I should write that somewhere. Since f is irreducible and f is c f0, either c is 1 or f0 is 1. Okay, technically f0 cannot be 1 because f0 is a primitive polynomial. What we really mean is that you can't factor it into, it is an integer by itself. But if degree is positive, f0 is not a unit, because f0 is a positive degree polynomial. In other words, c must be 1, because remember leading coefficient of f is positive. So any irreducible factorization of f must contain a unit. So either c is 1 or f0 is 1. Minus 1 is also a unit, but minus 1 cannot appear here because the leading coefficient is positive. In this case c is 1, so f is equal to f0. So f is automatically primitive. F is primitive, right? Because f0 is primitive. In this factorization, f0 is primitive and f is equal to f0, so it is primitive. So what is it that we have to prove now? We have showed that f is a primitive polynomial. We need to now show that f is irreducible in Qx. That's what we will show now. Suppose it's not irreducible in Qx. What does that mean? Suppose the next order of business is to show that f is irreducible in Qx. Suppose fx is not irreducible in Qx. What is the meaning of not being irreducible? If it's not irreducible, then there exists a rational polynomial h in Qx. I'm just repeating this. Rational polynomial, so h is in Qx, of positive degree such that h divides f, of course in Qx, right? If some polynomial is not irreducible in Qx, that means a positive degree polynomial divides it. So we can factor it. So I'm taking one of the factors, so that the other factors are not units. So the degree is positive and it divides f in Qx, because irreducibility is failing in Qx. So h divides f in Qx. Now what we can do is, so this in particular means, hence we can write hg equal to f for some g in Qx. That's the meaning of division, right? I recall this at the beginning of this video. If when we say h divides f, that means there exists a g in Qx such that hg equal to f. But now again we use our crucial proposition. Every rational polynomial can be written as its content times a primitive polynomial. So this implies c times h0 times g equal to f. I am just replacing h by ch0. ch0 g is equal to f. This implies h0 divides f in Qx only, I can say for now, because gc is only a rational polynomial for us. G is a rational polynomial, so h0 times cg is f, so h0 divides f in Qx. But what did we prove in the previous proposition? If a primitive polynomial divides another integer polynomial in Qx, then it divides that polynomial in Zx also. So, but h0 is primitive by construction, right? So, h0 divides f in zx itself. Right? If a primitive polynomial divides another integer polynomial in qx, that primitive polynomial divides that polynomial in zx. So h0 divides f in zx, but this violates, remember, this violates the irreducibility of fx in zx. Remember, what is the hypothesis? Fx is irreducible, right? Fx is irreducible in zx. But here what have we done? We have produced a polynomial of positive degree. Remember, when we divide it like, when we express it like this, degree of h is degree of h0. And h is a positive degree polynomial. h0 in other words is a positive degree integer polynomial which is a factor of f in zx. That means f is not irreducible. This contradiction shows that f is actually irreducible in qx. So all these things are a bit confusing, I think, and when you are seeing them for the first time especially. So you have to keep track of the results carefully. So if you need to, please see this video again so that all the ideas are clear in your mind. What did we show? We showed that if you take an irreducible integer polynomial with positive leading coefficient, then either it's degree 0, in other words it's constant, in which case it must be a prime integer. Otherwise it's a positive degree polynomial, then it is actually irreducible in qx. It's primitive and it's irreducible in qx. And now finally we are ready to show that zx is a PID. Sorry, zx is a UFD. So I'm going to prove this, and then I will, at the end of this video, I will revise the whole sequence of arguments. So finally our main theorem, zx is a UFD. This is the goal of this whole theory. The proof is, we already know zx is Noetherian, right? By Hilbert basis theorem, zx is Noetherian because z is Noetherian. So factoring terminates. Remember, in an integral domain, factoring terminates if the ascending chain condition on principal ideals stabilizes. In fact, in zx, ascending chain of condition holds for every chain of ideals, so it's a stronger condition. So factoring terminates. So to show that zx is a UFD, it suffices to show that every irreducible element in zx is prime, right? So this is also something we did in the previous video. In an integral domain where factoring terminates, that integral domain is UFD if and only if every irreducible element is prime. So that's what we are going to show. So we are going to show that every irreducible element of zx is prime. So in order to do this, let us take an irreducible element. You see where the previous proposition now will come in handy. So let f be an irreducible element. We have two cases. By the previous proposition, f is actually a constant, in other words it is degree 0, in other words it is in z, and f is a prime integer, right? So f is not the normal way of writing prime integer, so let's call it p. So that means f is equal to p. So this is case 1. So it's actually a degree 0 polynomial, in which case it's a prime integer. Suppose, so it is very easy here, but I will just go through the proof again for completeness. So what is the meaning of being prime? So actually I should call this case 1 by the way. What am I trying to show? F is irreducible. We want to show that f is prime. That is the goal. We want to show f is prime. What is the meaning of being prime? Prime means if f divides a product of two elements in zx, f divides one of them. So suppose f divides gh, where g and h are in zx. We would like to conclude that f divides either g or f divides h. So now, using again the big tool for us is that every polynomial can be written as a content times a primitive polynomial. So we do that here. G is equal to CG0, H equal to TH0. Okay, so we write it like this. G is CG0, H is DH0. So now F divides GH, that means F divides C, D, G0, H0, right? Because that's what GH is. So GH is C, D, G0, H0. So F divides that. But remember, G0, H0 are primitive. This implies G0, H0 is primitive. The product is primitive. Again, Gauss Lemma. So this is Gauss Lemma. What does that mean? What is a primitive polynomial? It means that the coefficients of G0, H0 have no common factor. So by the way, I have called F equal to P. So I'm going to stick to that. So actually maybe I'll write P. So P divides GH. So P divides CD, G0, H0. But G0, H0 is primitive. That means there is no common GCD of all the coefficients of G0, H0 is 1. That means there exists a coefficients. There exists a one of the coefficients. A is a coefficient of G0, H0 such that P does not divide. So what this is not properly stated but properly written. What I really mean is no prime number divides all the coefficients of G0, H0 because G0, H0 is primitive. So let us say there exists a coefficient A of G0, H0. So that's what I should say. There exists a coefficient A of G0, H0 such that P does not divide A. So think of G0 as a polynomial, G0, H0 as a polynomial, something x power n plus something times x power n minus 1 and so on. If P divides all the coefficients, G0, H0 cannot be primitive, right? So one of the coefficients is not divisible by P, so call that A. But P divides C, D, G0, H0. Remember the coefficient of C, D, G0, H0 one of the coefficients will be A, C, D. So P divides A, C, D. Right? So what am I really saying? This is very easy. G0, H0 is something times x power n, a n minus 1, x power n minus 1 and so on, a1x, a0. So one of these coefficients, so this is just explanation for this. One of these coefficients is not divisible by P. So let's say for simplicity that P does not divide a n minus 1. Then what is C, D, G0, H0? This is a n, C, D. C, D remember are integers. A n, because we are really dealing with integer polynomials. So the contents are both integers. So a n, C, D, x power n, a n minus 1, C, D, x power n minus 1 and so on. So this now is divisible by P because P divides the polynomial GH, which is actually CD, G0, H0. So the coefficients of CD, G0, H0 is CD, a n minus 1. So P divides ACD, but that means P is a prime number that does not divide A, so P divides CD. That means P again prime number, so P divides C or P divides D, but that means P divides C, G0 or P divides C or D, H0. That means P divides G or P divides. Okay, so that's all. It's a long argument for a very simple fact. If a prime so what I am really saying is a prime integer in ZX is a prime element. That's what we are saying, right? A prime integer is a prime element because we have taken two polynomials whose product is divisible by P, and we have concluded that P must divide one of them. So if it's confusing, please just go over this proof again, and it should be clear to you because it's not very difficult at this point. So suppose now second case, suppose degree f is positive. Remember again, I am trying to prove that any irreducible element in Zx is prime. So I have taken an irreducible element. By the previous proposition, it falls into one of the two cases. If it's in case 1, it is degree 0, in which case it's a prime integer. In case 2, it is positive degree. By previous proposition, fx is primitive. So fx is primitive and fx is irreducible in Qx. Right? So we know both of these facts. So any positive degree irreducible polynomial in Zx is primitive and it is also irreducible in Qx. So this is by previous proposition. This is really the only argument, only fact we need to know. The rest, as you will see, is very easy. By previous proposition, any irreducible integer polynomial whose degree is positive must be primitive and it is irreducible in Qx. Now suppose as before in case 1, suppose f divides gh where g and h are in Zx. I am trying to prove f is prime. That means I am trying to prove that if f divides a product of two integer polynomials, I will show that it divides one of them. Suppose f divides gh in Zx, of course, right? By which I mean g and h are in Zx. But this implies that f divides gh in Qx. This is not mysterious, right? What we know is that f times some f tilde is gh, where f tilde is in Zx. Because f divides gh in Zx means f times f tilde is in gh, but f tilde is also in Qx, because f tilde is in Zx, it's in Qx. The other way is not always true, and for that we need some hypothesis that f is prime, primitive and so on. But division in Zx certainly implies division in Qx. So f divides gh in Qx. But now f, this is what I should emphasize, f in Qx is irreducible, right? That I have said here. F is irreducible in Qx and Qx is a PID and hence Qx is a UFD, right? This is the sequence of arguments. F is a polynomial in Qx which is irreducible and Qx is, so this is end, a PID because it's a polynomial in one variable over a field. So hence a UFD, because a PID is automatically a UFD. So f is an irreducible element in a PID, so f is prime in Qx. So any irreducible element is prime. So f is prime, so f divides g in Qx or f divides h in Qx. In this step we are using the irreducibility of f along with the fact that Qx is a PID. We are using that f is irreducible in Qx, and if it is irreducible in a PID or UFD, it is automatically prime, so it divides the product, then it divides one of them in Qx. That is the important point. Now we are going to use the primitiveness. F is primitive. If a primitive integer polynomial divides another polynomial, it divides in, if it divides in Qx, it also divides in Zx. So f divides g in Zx or f divides h in Zx, and hence f is prime in Zx. Okay, so just let me review the proof. What am I doing? I am trying to show that Zx is a UFD. What we want to show is that every irreducible element in Zx is a prime element because Zx already is Noetherian. So factoring definitely terminates in Zx. So all we need to show is that irreducible elements are prime. Let us take an irreducible element and suppose it divides a product GH. F is irreducible, it divides a product GH. There are two cases. In the first case, F is actually a degree 0 polynomial, a constant in other words, in which case it has to be a prime integer, and we did that case here. A prime integer dividing a product of two polynomials easily implies that it divides one of the polynomials. That we have settled here in case 1. In case 2, we are treating the case degree is positive, and now by the previous proposition we have two important assertions. F is primitive and F is irreducible in Qx. So now if F divides GH in Zx, it certainly divides GH in Qx. Because F is irreducible in Qx and Qx is a UFD, F is prime. So F divides G in Qx or F divides H in Qx. Now F is primitive, says that F divides G in Zx, because if F divides G in Qx, F is primitive, so F divides G in Zx. If F divides H in Qx, F is primitive, so F divides H in Zx. So we conclude that F divides either G in Zx or F divides H in Zx, and hence F is prime. So Zx is a, okay, so this is the main result of this video and the last 2-3 videos to conclude that Zx is a UFD. So let me quickly review this before I make a generalized statement. What we have really done is we have essentially used the fact that the polynomial ring over rational numbers is a UFD, because that separately we know, because polynomial ring in one variable over a field is a PID, because we can use Euclidean algorithm to divide using the degree as our size function. So that is easy to prove is a PID, and a PID is UFD. We have settled all that. Now to prove that Zx is a UFD, what we want to do is basically use the fact that Qx is a UFD. In order to do that, we need to understand how to talk about irreducible elements in Zx versus irreducible elements in Qx, because to prove that something is a UFD, we need to show that factoring terminates and factoring is unique. In Zx, because it's Noetherian, factoring terminates automatically. There is no problem. Only thing to show is that factoring is unique, and for that the crucial observation is in an integral domain where factoring terminates, to prove uniqueness of the factorization, all you need to do is irreducible elements are prime. All this was done in the previous videos. So we want to show prime irreducible elements in Zx are prime. In order to do that, we have defined primitive polynomials which are by definition integer polynomials. We proved that Gauss lemma, which says that product of two primitive polynomials is primitive, and using the Gauss lemma, our important observation is that every rational polynomial can be written as a rational number times a primitive polynomial, and that is a unique expression. Once we have that, we are able to prove this very crucial observation that if you have two integer polynomials f and g, and f is primitive, and f divides g in Qx, f divides g in Zx. See, this is in general not true, that if two integer polynomials have this property that one divides the other in Qx, it doesn't mean that it divides it in Zx. We need the fact that it is primitive. So I will, in the next videos when I do problem sets, I will show why this primitive is important assumption. So this is supposed to be just a review. So let me quickly review this. So using this observation, we have characterized irreducible polynomials in Zx. They are either degree 0, in which case they are just prime integers, or they are positive degree, in which case they are primitive and irreducible in Qx. Using that, we have finally settled that Zx is a UFD. Okay, so all this is very important and somewhat confusing perhaps. So please make sure that you watch this again if you need to and understand this proof. This is a very crucial theorem in this whole course. And now, more generally, I will say this without proof. We can prove that if R is a UFD, then Rx, the polynomial ring in one variable over R, is also a UFD. Exactly the same proof carries over. R now will play the role of Z, and Q will be replaced by the field of fractions of R. Everything goes through. So you can, as a good exercise, You can step by step check all the statements and prove it in this general case. Hence, we can say by corollary, if R is a UFD, then R polynomial ring in any number of variables, finitely many, is a UFD. Okay, so because this is just like Hilbert basis theorem. If R is Noetherian, Rx is Noetherian. Then Rx, another variable, is also Noetherian. Similarly, if R is a UFD, Rx is UFD. So you can keep adding variables. At each stage you have a UFD. So in the next stage you are adding one more variable, it is a UFD. So this is the conclusion of this video. We have proved a very important result for Z and Zx, and it's not difficult to show that the whole proof carries over for any UFD. And finally you are able to show that if R is a UFD, R x1, x2, xn, a polynomial ring over R in finitely many variables, is also a UFD. So I'll stop the video here. In the next video we will do some more results, one of them being Eisenstein criterion using this circle of ideas, and then we will do some problems. Thank you.